Module 17, Lecture B, Bagging Embeddings. By the end of this lecture, you will be able to apply bagging classifiers and regressors with different base estimators, compare bootstrap, pasting, random subspace, and random patch strategies, and use random tree embeddings as feature transformations for downstream models. Bagging models. Bagging classifier. A bagging classifier improves classification by training several versions of the same model on different resampled datasets, then combining their predictions. Because each model sees a slightly different view of the data, the final vote is less sensitive to any one training example. This is especially useful for high variance models like decision trees, making predictions more stable and reliable in settings such as medical screening. A bagging classifier works by training multiple models on different bootstrap samples, so they tend to make different errors. Their predictions are then combined, usually by majority vote or averaged probabilities, to produce a more reliable final decision. This diversity and aggregation make the ensemble more robust to noise and outliers, helping it generalize better to new data. Bagging can use decision trees or other models that train on resampled data, such as nearest neighbor methods or support vector machines. The base model affects both performance and training cost. Because bagging mainly reduces variance, it works best with flexible models that learn real patterns but change across samples. If the model is too simple, bagging adds little benefit, so the goal is to balance flexibility, diversity, accuracy, and efficiency. Python code bagging classifier. This example trains a bagging classifier by building diverse decision trees from bootstrap samples. Combining their predictions through voting usually makes test accuracy more stable. We import key Scikit-Learn tools for building and evaluating a classification model. These include a function to create synthetic classification data, a bagging classifier to combine multiple models, and a decision tree classifier as the base model. We also use tools to split the data into training and testing sets and to measure performance with accuracy. We create a reproducible synthetic classification dataset using Scikit-Learn's make classification function. It contains 800 samples, each with 8 features, including 5 informative features and 1 redundant feature. The function returns the feature data and the target class labels. The code verifies that the number of feature rows matches the number of labels, so every training example has a corresponding target. If they do not match, it raises an error to signal the data mismatch. This check helps protect data integrity and prevents problems during model training. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. 30% of the data is kept for testing, while stratification preserves the original class balance in both sets. A fixed random state makes the split reproducible. We create a decision tree classifier with a fixed random state, so the results are reproducible. After training it on the feature and label data, the tree learns patterns it can use for prediction. This model provides a simple baseline for comparing more advanced models later. A bagging classifier is built by combining many decision tree models to improve performance. In this setup, 50 trees are trained on random bootstrap samples, each using 80% of the training data. This creates diverse models for a stronger ensemble, while fixed random states make the results reproducible. A bagging model trains an ensemble of decision trees using the training features and labels. Each tree is built from a random bootstrap sample of the data, selected with replacement. This creates diverse trees whose combined predictions improve the classifier's accuracy and stability. We compare a single decision tree with a bagging classifier by using both models to predict labels for the same test data. The decision tree relies on one learned model, while the bagging classifier combines predictions from multiple trees trained on different bootstrap samples. Comparing their results shows how the ensemble approach can improve robustness over a single tree. We evaluate both models by comparing their predicted labels with the actual test labels, using Scikit-Learn's accuracy score. This gives the proportion of correct predictions for the single decision tree and for the bagging classifier. Comparing these scores shows how the ensemble method performs relative to the single tree. We first show the Scikit-Learn version to support compatibility and reproducibility. Then we report the rounded accuracy scores for a single decision tree and a bagging classifier, making it easy to compare their performance. This script compares a single decision tree with a bagging classifier on a synthetic classification dataset. After splitting the data into training and test sets, it trains one tree as a baseline and an ensemble of 50 trees on bootstrap samples. Both models are evaluated on the test data, and their accuracy scores are printed along with the Scikit-Learn version. The bagging classifier usually performs better, showing how ensemble methods can improve stability and accuracy. Bagging regressor. A bagging regressor predicts continuous values by training several regression models on different bootstrap samples and averaging their results. This is especially useful for high variance models, such as decision trees, because it reduces overfitting and limits the effect of random noise. The final prediction is more stable, reliable, and less sensitive to fluctuations in the training data. A bagging regressor builds several models by training each one on a bootstrap sample of the original data, where some records may repeat and others may be left out. Each model learns slightly different patterns, then their predictions are averaged for a new case. This averaging reduces extreme predictions and makes results more stable and reliable, such as in housing prices, patient recovery estimates, or travel time forecasts. A bagging regressor works best when its base models are expressive and make diverse predictions across different data samples. It mainly reduces variance, so stable models or models that all miss the same pattern may gain little from averaging. For strong results, use meaningful features and base models that capture different useful signals, such as regression trees or other suitably variable models. Python code bagging regressor. Bagging can improve continuous prediction by averaging the results of many decision trees instead of relying on a single tree. This comparison typically shows that the averaged trees produce more stable predictions and lower test error. We import NumPy for numerical computing and use Scikit-Learn for machine learning tools. From Scikit-Learn, we bring in the make regression function to create a synthetic regression dataset for testing models. We import key Scikit-Learn tools for building and evaluating regression models. The bagging regressor creates an ensemble by training multiple decision trees on different data subsets and averaging their predictions, while the decision tree regressor provides a baseline model for comparison. We also use the train test split function to separate data for training and testing, and mean absolute error to measure how far predictions are from actual values on average. We create a noisy regression dataset using Scikit-Learn's make_regression function. It generates 600 samples with 6 input features, adds noise to mimic real-world data, and uses a fixed random state, so the results are reproducible. The function returns the feature data and the target values we want to predict. Before training, the code checks that the feature data and target values have the same number of rows. This ensures each set of features has a matching target. If the counts differ, it raises an error to prevent mismatched data from causing problems during model training. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is reserved for testing, and the remaining 75% is used for training. Setting the random state to 42 makes the split reproducible, which helps evaluate the model consistently on unseen data. We create a single decision tree regressor as a baseline model using a fixed random state for reproducibility. After fitting it to the training features and target values, the tree learns patterns it can use to make predictions on new data. We build a bagging regression model in Scikit-Learn using decision trees as the base learners. It combines predictions from 50 trees, each trained on a bootstrap sample, and uses a fixed random state for reproducible results. This averaging helps reduce variance and improve performance on new data. A bagging model trains several decision trees on bootstrap subsets of the training data. The trees learn independently, and their predictions are averaged to produce the final model. This reduces variance and helps the model generalize better to new data. We compare a single decision tree with a bagging model by using both to predict the test data. The single tree makes predictions on its own, while the bagging model averages predictions from multiple trees. Comparing the results shows how the ensemble performs against the individual tree. We compare a single decision tree with a bagging regressor by calculating the mean absolute error for each model. This error shows the average size of prediction mistakes in the target variable's units. If the bagging regressor has a lower error, it indicates that combining multiple trees improves performance over using one tree alone. The output reports the Scikit-Learn version for reproducibility, then compares model performance using mean absolute error. It shows the error for a single decision tree and for a bagging regressor, where lower error means better predictions. It also reports how many trees the bagging model uses, giving a sense of the ensemble's complexity. This script shows how a bagging regressor can improve predictions on a noisy regression problem. It compares a single decision tree with a bagging model that averages the results of 50 decision trees trained on different samples of the training data. On the test set, the bagging model achieves a lower mean absolute error, showing that averaging multiple trees can reduce prediction error and improve performance. The script also reports the Scikit-Learn version and confirms the number of trees used. Base estimator. In bagging, the base estimator is the algorithm copied and trained on different resampled versions of the data. These models make varied predictions, which are combined by voting in classification or averaging in regression. The base estimator matters because it shapes the ensemble's behavior, and bagging works especially well with flexible models like decision trees, whose predictions can change a lot with small data differences. Bagging can use decision trees, nearest neighbor classifiers, support vector machines, or other models as base estimators. It trains them on different samples of the data to create diversity, which helps the ensemble reduce errors. By combining votes or averaging predictions, bagging can make results more stable, such as in customer churn or housing price prediction. When choosing a base estimator for bagging, balance accuracy, stability, interpretability, and computational cost. Bagging is most useful for low-bias, high-variance models, such as deep decision trees, because averaging many versions can reduce their instability. More stable models, like regularized linear models, usually gain less. The estimator should fit the task and data, since it determines what each learner can capture, while bagging controls how many learners are combined and how their predictions are averaged. Python code, base estimator. Compare different base estimators within the same bagging classifier to see how the chosen learner affects performance. Bagging creates many copies of that learner, and test accuracy helps show which choice works better. We import key Scikit-Learn tools to build and evaluate bagging models for a breast cancer classification task. The dataset loader provides the data, train test split separates it into training and testing sets, and accuracy score measures performance. We also import the bagging classifier, using k-nearest neighbors and decision tree classifiers as base learners to compare how they perform in an ensemble. We load Scikit-Learn's breast cancer dataset, a built-in dataset for classification. The input features and target labels are then separated, preparing the data for later processing and model training. The code verifies that the feature data and labels have the same number of entries, so every data point has a matching label. If they do not match, it raises an error to stop training or evaluation before incorrect data causes problems. The dataset is split into training and testing sets using Scikit-Learn's train test split function. 1/4 of the data is reserved for testing, while stratification keeps the class balance similar in both sets. A fixed random state makes the split reproducible each time the code runs. We create a bagging classifier that uses decision trees as its base learners. The ensemble contains 30 decision trees, and a fixed random state makes the results reproducible. This setup lets us evaluate how bagging performs when decision trees are combined in the ensemble. A bagging classifier is built using k-nearest neighbors as the base model, so the ensemble combines multiple k-nearest neighbors classifiers. Each model uses 5 neighbors to make predictions, and the ensemble aggregates results from 30 such models. A fixed random state is used, so the results are reproducible each time the code runs. We train 2 bagging classifiers on the same training data, one using decision trees and the other using k-nearest neighbors as the base model. Each classifier builds multiple models from resampled versions of the data. After training, both are ready to be tested on unseen data to compare how well they generalize. To compare base estimators in a bagging ensemble, we measure the test accuracy of 2 models, one using a decision tree and one using k-nearest neighbors. Each model predicts the test data, and its predictions are compared with the true labels using an accuracy score. This shows how the choice of base estimator affects the ensemble's overall performance. The code reports the Scikit-Learn version, then compares bagging classifiers on breast cancer data using 2 different base learners, a decision tree and k-nearest neighbors. It prints each model's accuracy rounded to 3 decimal places. The main point is that even with the same bagging method, changing the base estimator can lead to different performance. So the choice of base learner matters in ensemble models. This script compares 2 bagging classifiers on the breast cancer dataset, using a decision tree for one model and k-nearest neighbors for the other. After splitting the data, it trains both models and measures their accuracy on the test set. The printed results, including the Scikit-Learn version and each accuracy score, show that the base estimator can change bagging performance even when the overall method is the same. Sampling strategies. Bootstrap versus pasting. Bootstrap sampling and pasting create diversity in ensemble models by training each model on a different subset of the data. Bootstrap sampling selects examples with replacement, so some may repeat and others may be left out, while pasting selects without replacement, so examples are only omitted. In bagging, this diversity helps the combined model make more stable and accurate predictions. Bagging creates varied training sets by sampling from the data with replacement, so some records may appear more than once, while others are left out. This is useful for unstable models like decision trees, because combining many trees can help their errors balance out. Pasting also builds diverse training sets, but it samples without replacement, so each selected record appears only once in a given subset. Bootstrap sampling and pasting both create varied training sets to help an ensemble generalize better. Bootstrap sampling allows repeated records, which increases diversity and supports performance estimates using records left out of each sample. Pasting avoids duplicates, making it useful when data is small, or each example is unique and important. The best choice depends on whether diversity or avoiding repeated examples matters more for the dataset. Python code, bootstrap versus pasting. Bootstrap and pasting differ in whether sampling allows replacement. With replacement, the same item can appear more than once in a sample. Without it, duplicates are avoided. The sample counts make this difference clear. We begin by importing NumPy, a Python library used for numerical computing. It provides tools for working with arrays and generating random samples, which are needed here to create bootstrap and pasting samples from the dataset. A small, labeled dataset is created with 6 items from A through F using NumPy. The sample size is also set to 6, so each sample can include the full dataset. This prepares the data for comparing different sampling methods. We use NumPy's default random number generator with a seed of 42, so the random selections are the same each time the code runs. This makes the results reproducible, which is helpful for demonstrations and lectures. A bootstrap sample is created by randomly selecting from the training examples with replacement. The sample has the same size as the original training set, so some examples may appear more than once, while others may be left out. This is the key idea of bootstrap sampling. We create a sample from the training examples by drawing without replacement, so no item can appear more than once. The random choice method selects 6 examples from the training set, and turning replacement off ensures every selected element is distinct. To compare bootstrap and pasting samples, we count how many unique examples each contains. A bootstrap sample allows repeated draws, so converting it to unique items shows how much duplication occurred. A pasting sample draws without replacement, so its unique count reflects the item selected directly. This highlights the difference in diversity between the two sampling methods. To find which original examples were left out, compare the full dataset with each sampled set. For both the bootstrap sample and the pasting sample, convert the examples to sets. Take the difference from the original set and sort the result for a consistent list. This shows which examples were excluded by each sampling method. The output compares the original training examples with 2 sampled sets, a bootstrap sample and a pasting sample. It shows each sample, counts how many unique examples it contains, and lists which original examples were left out. The key point is that bootstrap sampling can select the same example more than once, while pasting samples without repeats. This script compares bootstrap and pasting sampling on a small labeled dataset. Bootstrap sampling draws with replacement, so the sample may contain repeated examples and leave others out. Pasting draws without replacement, so each selected example is unique. The main point is that bootstrap can include duplicates, while pasting cannot. Random feature subsets. Random feature subsets train each model in an ensemble, using only some of the input variables. This random subspace approach changes the columns rather than the data rows, giving each learner a different view of the same problem. By making the models rely on different predictors, it helps diversify their errors and can improve the ensemble's overall prediction. Random feature subsets help ensembles work better with high-dimensional data, especially when many predictors are redundant or noisy. Instead of training every model on the same full set of features, each model uses a different subset, which encourages it to find different patterns. This reduces over-reliance on a few dominant variables and can reveal hidden signals, making the overall ensemble more diverse and robust. Using random subsets of features makes ensemble models more diverse and efficient. Individual learners may be slightly more biased because they see less information, but the ensemble often reduces variance and generalizes better. It also speeds training when there are many features. The key is choosing enough features to capture important patterns while keeping enough randomness to maintain diversity. Python code. Random feature subsets. Row and feature sampling are two ways to build diverse ensembles. Random subspaces train each learner on a different subset of features, and the resulting accuracy helps show how these sampling choices affect ensemble performance. We import NumPy for numerical work and Scikit-Learn for machine learning tools. The setup includes a function to create a synthetic classification dataset, a bagging classifier to build an ensemble of models, and an accuracy measure to evaluate predictions. We also split the data into training and testing sets, and use a decision tree with a chosen maximum depth as the base model for the ensemble. We create a synthetic classification dataset with Scikit-Learn to test sampling strategies. It contains 900 samples and 12 features, but only 5 features are informative, while the rest are noise. A fixed random state ensures the same dataset is generated each time, making the results reproducible. We first split the data into training and test sets, so every sampling strategy is evaluated on the same test data. Using Scikit-Learn's train-test split, we reserve 30% for testing, stratify by the target to keep class proportions consistent, and set a random state so the split can be reproduced. Before sampling columns, the code checks that the training data contains at least 4 features. If it has fewer, it stops with an error because the lesson needs enough feature dimensions for meaningful analysis and modeling. We create a decision tree classifier with a maximum depth of 4 to limit complexity and reduce overfitting. A fixed random state makes the results reproducible. This tree is then used as the base estimator for ensemble methods, giving a consistent basis for comparing sampling strategies. A strategies dictionary defines several ensemble sampling approaches by setting whether row sampling uses bootstrapping and how many features are sampled. Bootstrap rows uses bootstrapped rows with all features, while pasting rows uses non-bootstrap rows with all features. Random subspace samples half the features without bootstrapping, and random patches combines bootstrapped rows with half the features. This makes it easy to compare how each sampling strategy affects model performance. The code first shows the Scikit-Learn version to confirm compatibility and available features. It then prints a table header for comparing sampling strategies, including the strategy name, row bootstrapping, feature sampling fraction, and accuracy. The loop compares several bagging strategies by training a bagging classifier for each one. Each model uses 40 decision trees, trains on 70% of the samples, uses a specified fraction of features, and applies bootstrap sampling only when that strategy requires it. After fitting the model, it predicts the test data, calculates accuracy, and prints the strategy settings with the rounded score. This makes it easy to see how different sampling choices affect performance. This script compares how sampling choices affect a bagging ensemble built from decision trees. It creates a synthetic classification dataset, trains models using row bootstrapping, row pasting, random subspace feature sampling, and random patches, then measures test accuracy for each approach. The main takeaway is that bootstrapping and pasting change which rows are used, while random subspace changes which features are used, and these choices can influence ensemble performance. Random patch sampling. Random patch sampling trains each model on a different subset of both observations and features. It combines ideas from sampling cases and selecting feature subspaces, so each model sees a smaller, unique slice of the data. This is especially useful for large datasets with many examples and variables, and the ensemble combines these varied views to produce more stable predictions. Random patch sampling makes ensemble models more diverse while reducing training time. By training each model on different observations and features, it encourages them to learn different patterns and make different errors, which improves the value of averaging their predictions. It also helps when features are noisy or redundant, because no single model must rely on the full feature set. Random patch sampling works best when the patch size balances learning quality and model diversity. Patches that are too small may leave models with too little data or too few features, while patches that are too large reduce diversity and become closer to bagging. The right size depends on the dataset, number of features, estimator complexity, and redundancy in the data. This method is especially useful in high-dimensional settings, but on small datasets, it can become unstable by discarding too much information. This script shows how random patch sampling creates diverse training subsets for an ensemble. It generates a synthetic dataset with 120 samples and 8 features, then builds 3 patches by selecting different rows and feature columns at random. Each patch contains 66 rows and 4 features, and the printed results show that the learners receive varied observations and inputs. The main point is that random patches increase diversity by changing both the data samples and the features used. Embedding diversity. Out-of-bag prediction. Out-of-bag prediction estimates how well a bagged ensemble will perform on new data without using a separate validation set. Each model is trained on a bootstrap sample, so some observations are left out and can be used as test cases for that model. This gives a built-in measure of generalization, which is especially useful when the available data is limited. In random tree embeddings, out-of-bag predictions help evaluate whether the ensemble's feature transformations generalize beyond the data used to build each tree. Each tree partitions the feature space in a different way, creating features that can support models such as linear classifiers or regressions. By checking how out-of-bag observations are assigned to leaves across trees, we can judge whether the embedding captures stable structure or mostly random patterns. Out-of-bag prediction helps evaluate random tree embeddings by testing whether the ensemble works well on data not used to train each tree. Strong out-of-bag performance suggests the trees are not just memorizing samples, but are capturing different useful patterns. This provides an internal check that the embedding creates diverse features that combine effectively. This script shows how bagged decision trees can make out-of-bag predictions and create useful tree-based embeddings for classification. It trains a bagging model on a synthetic dataset, estimates accuracy using samples left out of each tree, and converts each example's tree leaf positions into one-hot embedding features. A logistic regression model is then trained on these embeddings and evaluated on a separate test set. The results compare out-of-bag accuracy with test accuracy and report how many embedding features were created, showing that tree embeddings can support effective classification. Random tree features. Random tree features use decision trees to turn raw data into useful categories, not just to make predictions. Each tree groups observations by the leaf nodes they reach, capturing combinations of traits such as customer behavior patterns. By using many randomized trees, this approach can represent complex and non-linear relationships without manually creating interaction features. Random tree features are useful because the trees are diverse. Randomness in samples, variables, or split choices makes each tree capture different patterns in the data, so the resulting features are less redundant and more informative. Downstream models can then combine these varied signals more flexibly and stably than relying on one complex model. Random tree features can be used as inputs to simpler models, such as linear classifiers or support vector machines, helping them capture nonlinear patterns. The trees create useful data partitions that reveal hidden structure in the data. In this way, a forest acts as an embedding tool that turns observations into richer features for better prediction. This script shows how random tree embeddings can improve classification on nonlinear data. It compares logistic regression on the original moon-shaped dataset with logistic regression after the data is transformed by random trees, which encode each sample's path through the trees as new features. The transformed features capture nonlinear patterns, leading to better accuracy. The main takeaway is that random tree feature transformations can make a simple linear model perform much better on nonlinear classification tasks. Bias, variance, diversity. Random tree embeddings transform data into a richer feature representation for models such as logistic regression or support vector machines. Instead of relying on one decision tree, which may be too sensitive or too simple, they use many randomized trees that split the feature space in different ways. Each observation is represented by the leaves it falls into, helping downstream models capture complex patterns that may be difficult to learn from the original features alone. Diversity in random tree embeddings helps because different trees capture different patterns in the same data. Each tree may split the data in a different way, so the model is not dependent on one unstable partition. By combining these varied views, the ensemble creates transformed features that let simpler downstream models learn complex relationships more effectively. Random tree embeddings balance bias and variance through how trees are built and how their features are used. More and deeper trees can capture detailed patterns, but may create sparse or noisy features, while shallower trees give broader, more stable signals. A downstream regularized model then selects and weights the most useful features, helping focus prediction on reliable nonlinear patterns and interactions. In this lecture, you learn to apply bagging classifiers and regressors with different base estimators, compare bootstrap, pasting, random subspace, and random patch strategies, and use random tree embeddings as feature transformations for downstream models. In the next module, Module 18, we will go over boosting stacking.
Thank you for your attention. See you all in the next lecture.